How's it going, guys? I am here with Comp 1805, and we're at our first lecture, which is on propositional logic. So let's just get right into it. A proposition is what is known as a declarative statement that is either true or false. The important part being that it's a declarative statement and that it has to be either true or false, but not both. So let's go through some examples. The first example I have here is 5 is a prime number. Okay, this is a proposition because it is declaring that 5 is a prime number, and we know that that it also is true because you can't divide 5 by anything but itself and 1. So it is a proposition. Yes. Is it true? Yes. Okay, now we have the word run is a noun. Okay. This is also a proposition because it's declaring a fact. It's declaring that the word run is a noun. Well, in fact, that we know that that's not true. So it's just a proposition that's not true. Now, finally, we'll use this example: is Taz a human being? Now, this is not a proposition. Why? Because I'm asking a question. I'm not declaring that Taz is a human being. I'm asking, is he one? No one will know, ever. So this is in fact not a proposition. And since it's not a proposition, why would it have a truth value at all? So that just leads me into my next definition here that says truth value. So the truth value is basically the value that's given to a proposition stating the fact that it's either true or false. So in this case, the truth value for our two propositions here are true and false. So that's as simple as truth value gets. Now, an atomic proposition is a proposition that where its truth value does not depend on other propositions' truth values. So it's a single statement by itself that declares a fact. And with these atomic propositions, we can actually make different formulas. These propositional formulas can then be translated into English, and then we can create sentences using propositional formulas. Now that's getting way ahead of myself, so I'm going to start talking about logical operators, which will be used to create these formulas. Alright, so let's start talking about logical operators. So what their purpose is to create new propositions, like I mentioned before. So let's just get right into it here. The first one I want to talk about here is negation. This is the symbol used to denote a negation. It's a little hooky thingy. I don't know what else to call it. So let's start off here. What its purpose is to take a proposition. So what I've done here is create a proposition P. It can be whatever proposition, I don't really care. So let's say P in its current state has a true value. P is true. Now let's add the negation symbol to it. Now P is false. So what this does is basically just gives the opposite truth value to what P originally was. And the way we can say this in English is not P. That's it. You just call it not P. So negation P equals not P. Another way to show how this works is using what's called a truth table. Now all you do to write a truth table is take your original proposition and then what you want its result to be, and then in the original proposition write out all its possible combinations. So in this case there's only two, and it's true and false. So now when we negate it, this just becomes false, this becomes true. And that's as simple as a truth table gets. Now, they're not always going to be that simple. And in fact, the next one even gets a little more complicated. So, now we're going to look at the logical operator AND. Now, with AND, what happens is that both P and Q must be true for the truth value of a P and Q to be true. So, first, let's draw to show how this works, let's just draw out a truth table. So we have P and Q, and then the result that we want, we can take this symbol I've drawn again, and we can call this P and Q. This is the result I want to get. So, when we add these together, let's put all the possible truth values that we can have for P. So we can have true, true, false, or false. And then if we have for Q, we can also do the same thing. True, false, true, false. How did I know that there was going to be 4 combinations? Well, to calculate that, all you have to do is take the number of variables you have, that is your n, and then all you do is 2 to the n is equal to your number of combinations. So in this case, 2 to the 2 is equal to 4. Alright, so now let's look at P and Q. So as you know, both P and Q must be true for this to be true. So, in this case, P is true, Q is true, this is true. P is true, Q is false, therefore this is false. Same thing for here, P is false, Q is true, this is false. And now they're both false, therefore it is false. That's it. That's all it takes for it. And one more thing I just forgot to mention. From now on, all of these things are called logical connectives. This is because they connect two propositions together. And that's just what the definition is. So now let's look at OR. OR, again, I've denoted the symbol right here. And what it is when P is true, or Q is true, or both are true, then P or Q is true. So you can see it in the truth table here. P is true, Q is true, therefore P or Q is true. P is true here, therefore P or Q is true. And over here, Q is true, therefore P or Q is true. And finally, both of them are false, therefore the statement is false. Alright, let's move on next to exclusive OR. Or, if you're lazy, you can just call it XOR or XOR. So, this is only true when only P or only Q are true. I spelled R wrong, true. So, now if we look at the truth table for this, here we see that P and Q are both true, therefore it's false. And then down here, they're both false, therefore the statement is false. Whenever it's just one of them are true, the statement is true. And that's how as simple as XOR gets. Alright.